In physical cosmology and astronomy, dark energy is an unknown form of energy which is hypothesized to permeate all of space, tending to accelerate the expansion of the universe. Dark energy is the most accepted hypothesis to explain the observations since the 1990s, indicating that the universe is expanding at an accelerating rate. Assuming that the standard model of cosmology is correct, the best current measurements indicate that dark energy contributes 68.3% of the total energy in the present-day observable universe. The mass energy of dark matter and ordinary matter contribute 26.8% and 4.9%, respectively, and other components such as neutrinos and photons contribute a very small amount. Again, on a mass-energy equivalent basis, the density of dark energy is very low, much less than the density of ordinary matter or dark matter within galaxies. However, it comes to dominate the mass energy of the universe because it is uniform across space. Two proposed forms for dark energy are the cosmological constant, a constant energy density filling space homogeneously, and scalar fields such as quintessence or moduli, dynamic quantities whose energy density can vary in time and space. Contributions from scalar fields that are constant in space are usually also included in the cosmological constant. The cosmological constant can be formulated to be equivalent to vacuum energy. Scalar fields that do change in space can be difficult to distinguish from a cosmological constant because the change may be extremely slow. High-precision measurements of the expansion of the universe are required to understand how the expansion rate changes over time and space. In general relativity, the evolution of the expansion rate is parameterized by the cosmological equation of state. Measuring the equation of state for dark energy is one of the biggest efforts in observational cosmology today. Adding the cosmological constant to cosmology's standard FLRW metric leads to the lambda-CDM model, which has been referred to as the standard model of cosmology, because of its precise agreement with observations. Dark energy has been used as a crucial ingredient in a recent attempt to formulate a cyclic model for the universe. Nature of dark energy. Many things about the nature of dark energy remain matters of speculation. The evidence for dark energy is indirect but comes from three independent sources: distance measurements and their relation to redshift, which suggest the universe has expanded more in the last half of its life. The theoretical need for a type of additional energy that is not matter or dark matter to form the observationally flat universe. It can be inferred from measures of large-scale wave patterns of mass density in the universe. Dark energy is thought to be very homogeneous, not very dense, and is not known to interact through any of the fundamental forces other than gravity. Since it is quite rarefied, roughly 10⁻27 kilograms per cubic meter, it is unlikely to be detectable in laboratory experiments. Dark energy can have such a profound effect on the universe, making up 68% of universal density, only because it uniformly fills otherwise empty space. The two leading models are a cosmological constant and quintessence. Both models include the common characteristic that dark energy must have negative pressure. Effective dark energy. A small constant negative pressure of vacuum independently of its actual nature. Dark energy would need to have a strong negative pressure in order to explain the observed acceleration of the expansion of the universe. According to general relativity, the pressure within a substance contributes to its gravitational attraction for other things just as its mass density does. This happens because the physical quantity that causes matter to generate gravitational effects is the stress-energy tensor, which contains both the energy density of a substance and its pressure and viscosity. In the Friedmann-Lemaitre-Robertson-Walker metric, it can be shown that a strong constant negative pressure in all the universe causes an acceleration in universe expansion if the universe is already expanding, or of deceleration in universe contraction if the universe is already contracting. This accelerating expansion effect is sometimes labeled gravitational repulsion, which is a colorful but possibly confusing expression. In fact, a negative pressure does not influence the gravitational interaction between masses, which remains attractive, but rather alters the overall evolution of the universe at the cosmological scale, typically resulting in the accelerating expansion of the universe despite the attraction among the masses present in the universe. The acceleration is simply a function of dark energy density. Dark energy is persistent. Its density remains constant, i.e., it does not get diluted when space expands. Evidence of existence. Supernovae. In 1998, published observations of type Iowa supernovae by the High-Z supernova search team, followed in 1999 by the Supernova Cosmology project, suggested that the expansion of the universe is accelerating. The 2011 Nobel Prize in Physics was awarded to Saul Perlmutter, Brian P. Schmidt and Adam G. Rees for their leadership in the discovery. Since then, these observations have been corroborated by several independent sources. Measurements of the cosmic microwave background, gravitational lensing, and the large-scale structure of the cosmos, as well as improved measurements of supernovae, have been consistent with the lambda CDM model. Some people argue that the only indication for the existence of dark energy is observations of distance measurements and associated redshifts. Cosmic microwave background anisotropies and baryon acoustic oscillations are only observations that distances to a given redshift are larger than expected from a dusty Friedmann limiter universe and the local measured Hubble constant. Supernovae are useful for cosmology because they are excellent standard candles across cosmological distances. They allow the expansion history of the universe to be measured by looking at the relationship between the distance to an object and its redshift, which gives how fast it is receding from us. The relationship is roughly linear, according to Hubble's law. It is relatively easy to measure redshift, but finding the distance to an object is more difficult. Usually, astronomers use standard candles. Objects for which the intrinsic brightness, the absolute magnitude, is known. This allows the object's distance to be measured from its actual observed brightness, or apparent magnitude. Type Iowa supernovae are the best-known standard candles across cosmological distances because of their extreme and consistent luminosity. Recent observations of supernovae are consistent with a universe made up 71.3% of dark energy and 27.4% of a combination of dark matter and baryonic matter. Cosmic microwave background. The existence of dark energy, in whatever form, is needed to reconcile the measured geometry of space with the total amount of matter in the universe. Measurements of cosmic microwave background anisotropies indicate that the universe is close to flat. For the shape of the universe to be flat, the mass, energy density of the universe must be equal to the critical density. The total amount of matter in the universe, as measured from the CMB spectrum, accounts for only about 30% of the critical density. This implies the existence of an additional form of energy to account for the remaining 70%. The Wilkinson Microwave Anisotropy Probe spacecraft 7-year analysis estimated a universe made up of 72.8% dark energy, 22.7% dark matter and 4.5% ordinary matter. Work done in 2013 based on the Planck spacecraft observations of the CMB gave a more accurate estimate of 68.3% of dark energy, 26.8% of dark matter and 4.9% of ordinary matter. Large-scale structure. The theory of large-scale structure, which governs the formation of structures in the universe, also suggests that the density of matter in the universe is only 30% of the critical density. A 2011 survey, the Wiggles Galaxy Survey of more than 200,000 galaxies, provided further evidence towards the existence of dark energy, although the exact physics behind it remains unknown. The Wiggles survey from the Australian Astronomical Observatory scanned the galaxies to determine their redshift. Then, by exploiting the fact that baryon acoustic oscillations have left voids regularly of ~150 mpc diameter, surrounded by the galaxies, the voids were used as standard rulers to determine distances to galaxies as far as 2000 mpc, which allowed astronomers to determine more accurately the speeds of the galaxies from their redshift and distance. The data confirmed cosmic acceleration up to half of the age of the universe and constrain its inhomogeneity to 1 part in 10. This provides a confirmation to cosmic acceleration independent of supernovae. Late-time integrated Sachs-Wolf effect accelerated cosmic expansion causes gravitational potential wells and hills to flatten as photons pass through them, producing cold spots and hot spots on the CMB aligned with vast supervoids and superclusters. This so-called late-time integrated Sachs-Wolf effect is a direct signal of dark energy in a flat universe. It was reported at high significance in 2008 by Ho et al. And Gian Antonio et al. Observational Hubble constant data. A new approach to test evidence of dark energy through observational Hubble constant data has gained significant attention in recent years. The Hubble constant is measured as a function of cosmological redshift. OHD directly tracks the expansion history of the universe by taking passively evolving early-type galaxies as cosmic chronometers. From this point, this approach provides standard clocks in the universe. The core of this idea is the measurement of the differential age evolution as a function of redshift of these cosmic chronometers. Thus, it provides a direct estimate of the Hubble parameter h equals -1, dz, dt -1, delta z, delta t. The merit of this approach is clear. The reliance on a differential quantity, delta z, delta t, can minimize many common issues and systematic effects, and as a direct measurement of the Hubble parameter instead of its integral. Like supernovae and baryon acoustic oscillations, it brings more information and is appealing in computation. For these reasons, it has been widely used to examine the accelerated cosmic expansion and study properties of dark energy. Theories of explanation. Cosmological constant. The simplest explanation for dark energy is that it is simply the cost of having space. That is, a volume of space has some intrinsic, fundamental energy. This is the cosmological constant, sometimes called lambda after the Greek letter lambda, the symbol used to represent this quantity mathematically. Since energy and mass are related by E equals mc2, Einstein's theory of general relativity predicts that this energy will have a gravitational effect. It is sometimes called a vacuum energy because it is the energy density of empty vacuum. In fact, most theories of particle physics predict vacuum fluctuations that would give the vacuum this sort of energy. This is related to the Casimir effect, in which there is a small suction into regions where virtual particles are geometrically inhibited from forming. The cosmological constant is estimated by cosmologists to be on the order of 10⁻29 grams per cc, or about 10⁻120 in reduced Planck units. Particle physics predicts a natural value of 1 in reduced Planck units, leading to a large discrepancy. The cosmological constant has negative pressure equal to its energy density and so causes the expansion of the universe to accelerate. The reason why a cosmological constant has negative pressure can be seen from classical thermodynamics. Energy must be lost from inside a container to do work on the container. A change in volume dV requires work done equal to a change of energy minus P dV, where P is the pressure. But the amount of energy in a container full of vacuum actually increases when the volume increases, because the energy is equal to ρV, where ρ is the energy density of the cosmological constant. Therefore, P is negative and, in fact, P equals minus rho. A major outstanding problem is that most quantum field theories predict a huge cosmological constant from the energy of the quantum vacuum, more than 100 orders of magnitude too large. This would need to be cancelled almost, but not exactly, by an equally large term of the opposite sign. Some supersymmetric theories require a cosmological constant that is exactly zero, which does not help because supersymmetry must be broken. The present scientific consensus amounts to extrapolating the empirical evidence where it is relevant to predictions, and fine-tuning theories until a more elegant solution is found. Technically, this amounts to checking theories against macroscopic observations. Unfortunately, as the known error margin in the constant predicts the fate of the universe more than its present state, many such deeper questions remain unknown. In spite of its problems, the cosmological constant is in many respects the most economical solution to the problem of cosmic acceleration. One number successfully explains a multitude of observations. Thus, the current standard model of cosmology, the lambda-CDM model, includes cosmological constant as an essential feature. Quintessence in quintessence models of dark energy. The observed acceleration of the scale factor is caused by the potential energy of a dynamical field, referred to as quintessence field. Quintessence differs from the cosmological constant in that it can vary in space and time. In order for it not to clump and form structure like matter, the field must be very light so that it has a large Compton wavelength. No evidence of quintessence is yet available, but it has not been ruled out either. It generally predicts a slightly slower acceleration of the expansion of the universe than the cosmological constant. Some scientists think that the best evidence for quintessence would come from violations of Einstein's equivalence principle and variation of the fundamental constants in space or time. Scalar fields are predicted by the standard model of particle physics and string theory, but an analogous problem to the cosmological constant problem occurs. Renormalization theory predicts that scalar fields should acquire large masses. The coincidence problem asks why the acceleration of the universe began when it did. If acceleration began earlier in the universe, structures such as galaxies would never have had time to form and life, at least as we know it, would never have had a chance to exist. Proponents of the anthropic principle view this as support for their arguments. However, many models of quintessence have a so-called tracker behavior, which solves this problem. In these models, the quintessence field has a density which closely tracks the radiation density until matter radiation equality, which triggers quintessence to start behaving as dark energy, eventually dominating the universe. This naturally sets the low energy scale of the dark energy. In 2004, when scientists fit the evolution of dark energy with the cosmological data, they found that the equation of state had possibly crossed the cosmological constant boundary from above to below. A no-go theorem has been proved that gives this scenario at least 2 degrees of freedom as required for dark energy models. This scenario is so-called quantum scenario. Some special cases of quintessence are phantom energy, in which the energy density of quintessence actually increases with time, and quiescence, which has a non-standard form of kinetic energy. They can have unusual properties. Phantom energy, for example, can cause a big rip,